Okay, today we will have a look on the deflection of determinate composite structure. We are still at chapter 1. In chapter 1, we are still dealing with the determinate, okay, structure. But the composite structure, what does that mean, composite structure? Anyone can help? Composite.
More than one material.
Thank you very much. Okay, composite is combination of more than one. More than one what? Maybe you talk about material, maybe you talk about types. Okay, so in this case, sometimes they use the word compound. Okay, so we are looking more about the types of structure. Okay, combination of different type of structures. So what we have learned previously, we have learned truss. Okay, we have learned beam, frame, arch. Okay, but now I want to classify these four structures into two types. Okay, one is dealing with bending moment, and another one is dealing with the axial forces. Okay, so here my lesson here will be talking about combination of these two type of structure, the axial force type and the bending moment type. Okay, if the beam is combined with the columns, okay, it becomes frames, right? So if a beam combined with the arch, it is still frame. Okay, so we don't say the composite structure like the beam with the arch is a composite structure in this case. Okay, I don't mean that. Okay, but if the beam and the truss, okay, then we will use this method to determine the deflection. Okay, I hope but we are going to use virtual work method only. This is our scopes. So the lesson outcomes, we are going to determine the composite structure that dealing with real load and virtual load. Again, because we are using virtual work method, we need to create two structures. Okay, to determine the deflection of a composite structure. Okay, so these are our lesson outcomes. And this, I'm going to explain one of the example here. Okay, this is a determinate system. Okay, you need to determine the vertical displacement at C of the composite structure. And the rod BD is being connected to beam AC at B. Okay, so meaning that this rod here, I shall name, maybe in your notes, can you name this BD is actually the rod. Okay, so this AC is actually the beam. Okay, they actually this rod connect to this beam hinge pin. Okay, but there is no hinge in the beam. I mean the connection that BD to beam is pin. Okay, so ignore the axial effect in the beam. So this is a very important statement. We are going to use it later. Ignore the axial effect in the beam. Okay, so the concept, if you still remember our deflection, okay, to determine the deflection for the truss structure, we use this N L over AE. And plus, if there is any due to temperature or any due with the this fabrication error, okay, and this will be applied for this axial force types of member, which is this rod. Okay, so and we have also for formula for determining the deflection for bending type, which is for beam, frame, and for the arch. Okay, so this will be dealing with the integration. Okay, m over ei. Okay, dx. So now, if we want to determine the deflection, okay, for this composite structure, what can you guess? What shall we do?
Madam, I cannot see the slide.
Huh?
I cannot see the slide.
You cannot see the slide. All right, so cannot see the slide.
This slide, madam.
Can you see the slide? Yes.
Example 1.
Deflection of determinate composite structure.
Yes, I can see.
Yes, we can see.
All right.
Okay, madam.
Okay, so this is the topic of our lesson today, and then just now I'm here. Example 1. Okay, so we need to determine the vertical displacement at C of the composite structure. So as I mentioned just now, we have need to have a combination, okay, of this different type of structure. Like for example, here we have a rod. The rod is usually having, is not usually, is having only axial force. Okay, so we will use this delta to determine any this equation to determine any of dealing with this axial force type of structure, like for example truss, and including this rod or cable or struts. So you need to use these deflection equations. And dealing with bending moment type of structure like beams, frames, okay, you are going to use this. Okay, so now my questions to you is, if now I have such composite structure where I combine this rod and also the beam, so what is the modification to these equations? Okay, we plus it, we just plus it. So today we will have a look, okay, how to determine the vertical displacement of this composite structure at C. Okay, so because they are dealing with this axial force type of structure, bending type of structure, so we just sum it up, this deflection value. Okay, so let's have a look. Okay, first of all, we create this structure that we not create, we just use directly on the from the real problem, where this structure is dealing with the real load 10 kilonewton. Okay, we can name this structure right now. Okay, M, big N. Okay, M is a moment type, N is the axial force. Okay, so we can look at this. Oh, I put a blank in your notes. Maybe you need to take some papers to work with me on how to get the support reactions for this real structure. Okay, so there is not much different from what we have learned before, okay, because we are still using the equilibrium of the whole system and equilibrium of a cut section and equilibrium at the joint, okay, to solve this composite structure. So now in this case, we are going to choose the first one. Okay, I consider the whole system. Means that I do not cut any system. I do not cut any section here. Okay, so ax, ay, dx, dy, the answer is already given here, but we need to determine it. So what we can do it now here is we take a summation moment. Let's say it in my here, I think I take a equal to 0. Okay, is it? Can I go to, yes, okay, I take summation MA equal to 0. So clockwise, let's say, okay, so now the forces that will give a moment to A will be dx and also 10 kilonewton. Okay, so let's try. So 10 kilonewton, the distance to A will be 6 meter. Okay, acting clockwise, positive. And then dx will be, the distance is 1. okay, and acting counterclockwise. Okay, so equal to 0. Therefore, my dx is equal to, can anyone help? Yes, so 60 kilonewton. So it is positive, meaning that my assumptions going to this direction is correct. So here we have 60 kilonewton here. Okay, then we can use the summation Fy equal to 0. Okay, so no, summation Fx. Okay, so I have Ax. Sorry, Fx is going horizontally. Ax positive, dx negative. Okay, what else? We don't have any others, so we can directly put equal to 0. So Ax is equal to dx is equal to 60 kilonewton. So again, this is positive, meaning that our assumptions direction is correct. So now we have dx and Ax solved, but we cannot solve for Ay and dy for this whole system. Therefore, we can use other method. Either you cut section, or either you considering here, I choose the second process here, is to consider the joint. Okay, treat it just like if you a method of joint in your truss analysis. So we put all the equilibrium, all the forces acting at the joint D. So now at joint D, if you look at here, okay, you need to focus, look at joint D. So now joint D, I have dx 60 kilonewton, okay, drawn at the exact direction. Dy is my assumed direction, and dB, I assume it tension, okay, and I also determined, okay, the angle, okay, of this 26.565 degree. So now you can start using the summation F. Which one you want to first? Summation Fx or summation Fy first?
Fy.
Summation Fy first.
Yes, yes.
Okay. If you have summation Fy, you are going to have two unknowns, right? dy and ndb. You can do it, but creating this equation will not give you answer yet. Okay, so I will start at x first. Okay, there is no problem if you want to start y first, but that equilibrium will not give you directly the answer. Okay, then you need to solve for summation fx. So now if I put the summation fx first, then I have only one unknown, because n dB cos 26.565, okay, and then minus 60 equal to 0. So here I can directly solve for n dB. Anyone can help? Where is my answer?
57.
Sorry, again? 50?
57.
57, huh?
60.
60.
67.
67. Am I right?
Yes, yes. 60.
Okay. 60. Okay. 67 kilonewton. Okay, so this is tension. So then I can proceed with summation Fy, because I still intend to get my dy. Okay, so, okay, here I also forget about this. Okay, so now dy plus minus n dB sine 26.565 equal to 0. So here I will get my dy. Can anyone help? You can substitute this n dB into this system.
30.
30. Okay, so you get the answer 30. Okay, and it is positive. It will be exactly like what you have assumed earlier. So now you left only ay. So you can put the summation Consider back to the whole system here. Summation Fy equal to 0. Okay, so I have dy minus ay equal to 0. And this, I want to find ay must be equal to dy must be equal to, oops, missing something. Anyone can help on here in this system?
10, negative 10.
Thank you, minus 10. So ay will be equal to dy minus 10. It will be 20 kilonewton. Okay, so this is how you do it. Okay, exactly like what you have assumed here. Okay, so you have solved for all the support reaction. So all these planning or strategy, you need to decide. Okay, either you want to cut a section, you can cut a section. There is no problem. Okay, as long as you can get this answer. Okay, so I will. Is that okay with this? Have you take down the notes? Okay, because I'm going to move to the virtual structure. So for the virtual structure, we have name it small m and small n. Okay, again, we need to determine the support reaction. Okay, but now if you look at this system, real structure is acting 10 kilonewton, okay, at C. Okay, and now the virtual structure, 1 kilonewton acting at C. So when this load is acting at the same location, and all the geometry and support conditions are the same, so therefore you can just use the proportionate method. So now this is 10 kilonewton become 1, so everything is just to divide by 10. Okay, so meaning that you do not need to proceed again all your these support reactions process. You just need to take whatever from the real structure, divide by 10. Okay, so this will be your support reaction for the virtual structure. But make sure the loading must be acting the same, okay, at the same location. Okay, only you can do that. If this 1 kilonewton is here, so I'm sorry, no, you need to redo it. Okay, so are you okay on these slides?
Yes.
Okay, so we are just using a proportionate method. Okay, and all the support reactions just to divide by 10. Okay, because the 1 kilonewton acting the same exactly like the real structure, just divide by 10. Okay, so once you have determined the support reaction, what's the next? We go back to what actually our problem. We need to determine the vertical displacement, and we need to use this equation. So meaning that we need to gather anything about axial force and anything about the bending moment. Okay, so do you have any bending moment in the rod? What is the internal force in the rod?
Tension force?
There will be axial force. Will it have this bending moment?
No.
I don't think so, madam.
Thank you. So there will be no bending moment in the rod. Okay, only axial force. The rod can be either tension or compression, but in this case it's tension. But cable will be always in tension. Strut will be always in compression. Okay, sometimes they use rod or bar. Then you need to determine whether it is in tension or compression. Okay, how about in the beam? Do you have bending moment in the beam for the internal forces?
Yes.
Yes. So internal forces in the beam is, can you list for me what are the internal forces in the beam? Meaning that when you cut a section here, what you draw? You have bending moment. What else?
Shear force.
Shear force. What else? Axial force.
Yield force.
Yes, axial force. So as we have mentioned earlier, axial force not usually happen in the beam. Okay, if you do not have any horizontal load. Okay, but now you have a horizontal axial force, right? This FBD, right? So this is actually sloping load, which it can resolve into also a horizontal load. So the end in the beam exists here in this case. Do you get what I mean? So in this beam, we have shear force, bending moment, and also axial force. Okay, but now in this problem, it said ignore the axial effect in the beam, meaning that in this beam, it asks you just to ignore this. Maybe it is just not significant, okay, compared to the whole this behavior. Okay, so you need to read this. If this statement is not here, axial effect you need to consider, meaning that you need to consider this n later. Okay, meaning that you need to put this n also in the calculation of this NL over AE. Okay, so let's have a quick look on next steps. Okay, now we need to determine the internal force. We will solve for n first. Okay, we intend to solve for n first. Okay, so here, I think we already solved for the n, right? Just now you have solved for this joint D. Okay, the n dB just now you have obtained is 67. Let me check. Yeah, 67. You have solved the joint, and then using the similar action here, you can solve for the small n. Okay, but because this is you can use the proportionate method as well, which you just divide by 10 here. Okay, or if you are not confident with that, whether it should be divide by 10, redo this statement. I mean, redo this equilibrium at joint D for this virtual structure. You will get 6.71. Okay, you can try that. Are you okay with this slide?
Okay, madam.
Okay, because now we need to gather all the information for our equation. And the equations requires the n, the axial force. So we solve for all the axial force first. Okay, but because the beam, the effect of this axial, okay, has been ignored. So therefore, we do not find any of these axial force in the beam. Okay, next, we need to find bending equation. Okay, bending equations mean that you need to cut section. So in this case, how many section you want to cut? Let's see the real structure.
Two.
Yes, thank you. So we do not need to cut the rod because we know that the rod is, there is no moment at all. But the rod has this F, the NBD. Okay, so there will be some differential in terms of loading at B here. So therefore, you need to cut two sections here. Okay, so similarly, you will cut two sections, okay, for the virtual structure. And then you need to decide this section 1, let's say, where do you want to consider either the left part or the right part? Okay, probably since you already determined the support reaction, okay, you might want to get from here, X1. Okay, so let's try, okay, to get this. So you actually do not need to have a look on this at all. Okay, this is not in your system. You just need to focus here only, right? Because you are focusing your X1 starting from for this left section. So now if I draw this free body diagram out, it will be something like this. 20, 60, and then bending moment. And then this is x1. So what is my bending moment here? We'll write M equal to the force that will be acting at this x will be 20 only, right? So there'll be 20. To get the moment, we need to multiply with the distance, x1, right? So this sign is positive or negative?
Positive.
Positive, positive.
So it is actually negative.
Hiya.
Ayah. Actually, what you have practicing is like this, right? Summation moment at x equal to 0, right? So you are considering clockwise as a positive sign. Okay, so this moment will be actually negative moment, right? And then this 20 will be negative 20x1, right? Right? So this M1, I need to rearrange such that M will be equal to negative 20x1, right?
Yes, madam, yes. I'm sorry.
Yeah, so be careful on this. Okay, so the next thing will be the cut section 2-2. Okay, the cut section 2-2, for me, I will decide start from C. Okay, x2. Because I just need to tackle this 10 kilonewton. So I do not draw the free body diagram here. I just imagine the whole left side is known in my sight. Okay, so this will be my moment. Okay, so now I have only 10 kilonewton and then my x2. So now, what is this sign? Positive or negative?
Wait, negative.
Negative.
Negative. Yeah. So if you're still following my previous lesson, we give a tips there, right? Actually, the fundamental is from here. Okay, but when we want to do a quick one, so maybe it will be, you will start to confuse. So you make yourself a simple rules created by yourself. You may want to follow mines. Mines is if this 10 kilonewton is acting the same, the direction, the moments, is acting the same with this internal moment here. Okay, so right now 10x2 is actually acting the same, right? Clockwise, right? Then you will get a negative. If it is acting opposite, then it get positive. Okay, so let's try again here. Okay, so now I'm considering I must considering the same x1 and x2. Okay, so here you be negative 1x2. Okay, this will be negative 2x1. Oops, I enter my own. So once you have obtained your this M and virtual M for your virtual structure as well, you need to also look at the range. Okay, so let me discuss. So now, just now my x is starting from A here, x1. So my maximum is actually up to B. So therefore my range for the x1 is up to 2 meter. And for my cut section 2, my x2 is starting from C. And my max will be up to B. Okay, therefore my x2 will be from 0, where I measure from C, and up to B is 4 meter. So this range must be input correctly. Okay, here I have purposely put alternate 1. Okay, because some of you might I don't want my cut section 2 where my x2 start from C. I still want to start from A. Then what should I do? Okay, this is what you expect. Okay, so now I will cut the section for, it will be still the same, 1, 1, start from A. Okay, but now I want my 2, 2 still start from A. So my x2 is here. So what cut section x2 start from A, meaning that you are looking at the left section. So now at B, you cannot forget about there is some reactions here happening at B due to this rod. Okay, so how this reaction, okay, at B, coincidentally, okay, is actually same with this the direction same with at D, the dx and dy, the direction. Okay, if you want to go very details and see why it's have this direction, you need to go to the this free body diagram. Okay, so this is a rod at D. The direction at D, okay, is this way. So come to B, for this system, it will be opposite direction of the Y component and X component. And come back to the joint B at beam, okay, it will be again like your D direction. Okay, therefore you have these reactions here in this direction. Okay, maybe you can take these notes down. Okay, why this B is in such direction. Okay, so now you already have this 30 and 60 kilonewton. This 30 kilonewton will be also incorporate in finding this moment at number 2. Can we try? Okay, so if this is just too messy for you, cannot see at all, yeah, you can draw your free body diagram. So now for this x2, you have A, you have B, okay, and you have a cut section, and you want to find M2. And at A, you have 20 kilonewton. The 60 kilonewton will not affect anything, but at B, you have 30 kilonewton. Okay, so now we can draw these bending moment equations M2 directly. Okay, so now I know that 20 kilonewton. Okay, what is the distance to cut section? May I know?
2.
It will be x2. Okay, because this cut section, we never know where is the location. Okay, it can be here, it can be here. So this x2 is actually the distance from A to the cut section. Okay, so A from B is 2 meter, right? How about now 30 kilonewton to cut section? How much is this distance?
Six.
No, If you can see, maybe my drawing is not that good. Let me try again. Draw one more. Okay. So this is, oh, it is worse. I tried my best. Okay. Now here, this is A, this is B. A, I have 20 kilonewton. Okay, B, I have 30 kilonewton. Okay, this is my cut section somewhere around BC. I don't know where. Okay, but I can know that my A to this cut section, the distance is x2. Okay, so and I know that A to B, okay, the length is 2 meters from the system. So now from this B to the cut section is how much? The distance.
X2 minus 2.
Yeah, so next time I will draw better my free body diagram. X2 minus 2. Okay, so now you have know all the distance. We can start to get my M2. Okay, M2 first is due to 20, right? So I will write 20 force and my distance to X is X2. Okay, so now negative or positive, in this case, it is acting the same direction with my internal moment.
Positive.
So it is negative. Okay. So if you want to use the shortcut like this, so if it is same direction, we put a negative. If it is opposite direction, we put a positive. Okay, because we are bringing this moment to the other side of the equation. If your early style of written the equation is the same sign, you put the same direction, you put the same sign, right? Like for example here, negative m minus 20x. If you are putting summation mx equal to 0 earlier and making sure this is clockwise is positive, you are deriving negative m minus 20x1. So if you can see that you are actually using the same sign. But now I want to throw this to the other side of my equation. So it will be opposite sign with your moment. Okay, so let's try again. Okay, so now I want to have find my moments due to 30 kilonewton. Okay, so it will be 30 times the distance is x2 minus 2. Okay, so now what is the sign for this 30 kilonewton? Yeah.
Positive.
Yes, because it acts opposite to our internal moment, so it will be positive. So this is how your bending moment equations for this alternative 2. Okay, let us have a look. Am I taking too much time? Let me check the time. Oh, it's already 9. Okay, so this is how you get your bending moment equations, but remember your range also different. Okay, the range for CB, oops, should be, I will name it BC right now. Okay, so the range for BC is from the x2 is from 2 to 6 meter, because you just concerned about the equations start from B to C. Okay, be careful about that because this range is very important. Okay, the equations for AB negative 20x apply only from 0 to 2 meter, while the negative 20x plus 30x2 minus 2 applies for 2 meter until 6 meter. Okay, you need to be very sure on that. So either one of any this alternate, you still get the same answer. Okay, you can put your this substitute this x value into this. Okay, you will get the same value for both of these cases. Okay, but be careful lah. Your x2, this 2 meter is talking about B here. Okay, but this 4 meter here is talking about B. So be careful when you want to substitute the B and check on the alternate idea 1 and idea 2. You need to know where is B. In this case, alternate 1, B is at 4 meter. So therefore, you substitute 4 in, okay, it get negative 40, right? But come to here, okay, the X is 2. So when you substitute 2 in, you shall get the same answer with negative 40 just now. Okay, so next is our important step where we apply the virtual work equation. Okay, this is my obtained n value. This is my obtained bending moment equations. So what we can do to determine the deflection at C is to combine, okay, these two effects, the NNL over AE and also MM over EI. So now NNL over AE, you got this N, right? N, and then you put it in, and the length for, please put it another one in your table maybe. The length for dB is this, okay, over AE. So you solve for this effect due to the rod. Then you can proceed with the beam, okay, AB and CB. Okay, for AB, this is for AB. Maybe you can snap this patch, okay. For AB, we have small m, capital M, just put it in, okay, from 0 to 2 meter. Okay, and then for CB, this is for CB. Okay, negative x and negative 10x, and from 0 to 4. Okay, then you can solve, okay, by your calculator. Okay, all these from the fraction, from the integration. Okay, this is what you have. Okay, if the AE and EI is not given to you. If the AE is given to you, EI is given to you, just put it in. Okay, the equations, you get the exact value of your vertical deflection at C. Any question, class? I show you the step on how to tackle if you have this composite structure. Any question for me?
Madam, how to find the value L?
L. The L will be the length of this dB. Okay, so let's go back to our length. Okay, our system is this one. So this is the length, hypotenuse. Okay, we have 2, we have 1, right? To get this length is 2 squared plus 1 squared. Okay? Okay. So any other questions for this? Okay, if the exert effect is not ignored, you need to consider that. What you need to do? You need to sorry. Okay, it's here. You need to add another 2 more member here. Okay, which is dealing with the beam. Beam has AB and BC, right? So you need to fill in this member AB. and also member BC. Okay, so then you need to put in what is the axial force in this member AB and what is the axial force in this member BC. Okay, for example, in this case, okay, we know that this is, then you treat it just like truss. Okay, so now you have this solving the joint A. So joint A, you will have this 60 kilonewton AX. Okay, so therefore the forces for this AB will be like this. Okay, this will be 60 compression. Okay, for AB. Okay, then you go to C. Okay, at joint C, you don't have any horizontal, right? So definitely here, the axial force is 0. Okay, you solve joint by joint. Okay, I repeat now for virtual structure. Okay, for beam AC, you want to solve for axial force, right? You can just solve like your this method of joint. Okay, you look at this joint A. Okay, joint A, you have 6 kilonewton. Okay, so to counterback this force, you will have the other force coming this way. Okay, so it will be -6 because the arrow going into the joint, compression. And then you can move to joint C. There is no horizontal force here. Okay, therefore here the CB is also equal to 0. Okay, so now you have obtained this n and this small n. You can put it in the -60 and -6. You can put it in the table just now. So here will be, oops, -60, -6. Okay, what is so difference from here is later you need to add here. Okay, for the beam. This is for the rod, right? Then you need to add another one for the beam. So meaning that this one, the equations will have to determine from the rod and also from the beam. Okay, so let's have a look if we want to incorporate this because the other is 0, right? So we can ignore just because there is no results from here. So we have -60, -6, and then the length is 2 meter over AE. Okay, this is the extra, yeah, you can try to determine this, whether it has significant change in your results or not. Okay, you can try that later. Okay, do you understand my explanation?
Yes.
Okay, yeah. So, but I couldn't remember why I have another page on this. May you check later what is happening on this page because I've already sent you the notes. Just give me a feedback on this later. So yeah, today actually I would like to share another solution. On the arch problem with you. Maybe we take 5 minutes later. Okay, let us have a break of 5 minutes. Then I will be drawing the arch problem for us to try. To try. This is taken from the final examination question as well. Okay. Okay, let's take 5. Okay.
Okay, madam.
Okay. So let me see your attendance. Oops. Arif? Hi, Arif.
Here, madam, on the way. Sorry.
Yeah. Okay, can we start class?
Yes, madam.
Yes.
If you get this question for your test, can you answer? Not sure, huh? But we have learned this in our last week on the arch, okay, on how to get the bending moment. Is that a composite structure, this one?
No.
No.
Yeah. This is just a frame, okay? Or maybe not so straight beam. It actually acts like a cantilever beam. Only it has this component, a shape of this arch. Okay, so we are going to take this practice this today. Okay, so I hope but I'm not going to take directly the this problem. I prepared one for this problem. You may try it later. Okay, your own. I want to change this to please help me to change this to 10 kilonewtons so that we can get a real feel of this structure. Okay, so this I put it at 3 meter. Okay, this one I put it at 3 meter. Okay, actually it's still the same. Okay, if you have putting in this R or P later, you just put it. I mean, the equation is not solved. This will be in terms of this P and R. Okay, so now this is my question. Okay, let's try what we need to do first. Have you taken this question?
Yes.
Okay, yeah, because I want to go to the next slides. Maybe how to write? Maybe I shall put it this way. Wait, I need to be quickly this. Oops. How to this is okay, this is 10 kilonewton. P is equal to 10 kilonewton, and then is equal to 3 meter. Okay, so let me just put it for you first. Okay, so it's in your chat room if you want to, cannot see it very clearly. So now I'm going to start on how to solve this. Okay, so we are going to create the real structure will be directly this one. And the structure will be this one. And then my virtual structure. Can you try to draw your virtual structure as well? Okay. So this is your real. What is our question? Okay. Vertical deflection at A. Oops. Oh, then you can still use the proportionate method. Huh? Okay. So now, how should I modify this? Okay, I can copy and paste it here. This cannot. My goodness. It takes some time. How to get this tree here? No, why? move the okay, so this is your virtual structure, and still 3 meter. So I hope you can draw this virtual structure and the real structure. So let's name them real structure with this M, and then I have my virtual structure. Small m. Okay. Then I need to cut the section. So now this BC, since it is not the straight line as AB, you need to also cut one more section. Okay, so there will be a total of 2 cut sections here. Can I use my pen now? Do you see my screen on this example arch?
Yes,
Yes.
madam.
Oh, okay.
Yes, yes.
Yeah. So now we are going to cut 2 sections. One is in between AB and another one is BC. So, mana saya punya pen? Why my pen won't? Should I put this? But why? I need to go back to see my setting. Why? Crazy. Okay. Know why my pens become like this, small. Can I change it? Okay, let's try again here. Still cannot. Why it is not doing well? All right. So I will use this. And how today? This is what my cut section, and I need to decide where is my X, okay, or left part or right part of the cut section I need to do. Okay, so here I put all my X starting from same. Okay, one is from here. I have to use this first. Okay, my X1. Okay, this is 1, 1. Okay, this is my 2, 2. Okay, I start my B from, try to start, remember your X shall be parallel with your member. Okay, so since AB and BC is not parallel, so try not start your X for section BC from A. Okay, that will be very tricky. So now your X2, you can start it from here. Okay, similarly for your X1, Okay, try to always put your X start from that and parallel with the member. Okay, and for number 2, okay, so this is how you do it. Okay, so next we need to cut a section M. Okay, so okay, but I want to put in the table. Okay, I hope I can draw a good table later. So now let us try to solve for this first. Okay, I'm going to consider this left part. Okay, and my moment M1 here will be actually equal to, okay, I have only deal with this 10 kilonewton in this left part, and I will just put 10. Okay, and the distance is x1. Okay, since this 10 kilonewton acting same direction with my this internal moment M, okay, it is negative. Okay, done. So now I see this is quite simple. I will just directly move to my virtual structure, okay, because it's will be acting the same. I'm considering now the virtual structure. Okay, take remove all my real load, apply 1 unit load to the system at where you want to determine the deflection. So in this case, we need to determine the deflection at A vertically. So we put the 1 kilonewton acting vertically to A. So now here I can get my small m here with the loads 1 multiply with the distance x1. And it is again same direction with acting with my internal moment here. So it is negative. Okay. So what happened? Okay, so done for section 1. Now I want to do for my section 2. Okay, my section 2, if you look at here, I'm also considering the left part. Okay, when you are considering the left part, can I save this first? Okay, when you are considering the left part, meaning that you are actually considering the whole things, this one. If you want to draw the free body diagram. Okay, you are considering like this. Okay, whatever loads forces on this system, you need to put it in. Okay, so now my x2 is running in such. Okay, and if you still remember in our this arch system, we actually not exactly using this x, the distance, okay, but in terms of theta, okay, in terms of this theta. So we are actually moving our range, writing our range in terms of theta from 0, okay, up to here is how much, but in radian. Okay, so I would like to go back to this x first. X1, the range is from 0 to 3 meter. And now the range for this cut section 2, we are referred to this theta. Okay, so this theta will be at the range from 0 to 90 degree, right? So 90 degree, if you want to write in radian, it will be pi over 2. So this is the range. Okay, for member B, C. This is the range for member A, B. Okay, so now because we want to, even though this range, we are looking at this theta, because we are going to use this cos theta or sin theta in our equation. Okay, but when we deal with this getting a moment, we're still looking at the distance that perpendicular to the loads. For example, the distance perpendicular to the loads from this 10 kilonewton to this one, okay, is this distance. So now we need to get what is the how to say, what is the length, okay, here, this one. So how to get it? Okay, if you still remember, okay, we have this, maybe I draw a bigger one, okay, where you have this, this is R, right? So now if you draw a triangular here system, okay, so you have a theta, you can get this value, this base of this triangle, R cos theta. Okay, you can get the height of this triangle, R sin theta. Okay, but in this case, we just require the horizontal components. So we will use the R cos theta. So you know that when come to here, okay, so we can know that this distance is actually 3 cos theta, R cos theta, right? Can you see the triangle here? So this is 3 cos theta. So how about here? Sorry, this one is not.
R minus 3 cos theta.
Thank you very much. Because you know that the whole things from A to O, let's B to O, let's say, this is R, right? The radius. Okay, so you know that B to O is 3 meters. So now, but you have calculated that from this arrow is 3 cos theta. So here will be 3 minus 3 cos theta. Okay, so what are our intentions here from 10 kilonewton to this is how much then?
6 minus 3 cos theta.
Thank you very much. Okay, I think my drawing, I hope it will not. Okay, so now from here, you just need to sum up this 3 meter plus 3 minus 3 cos theta. Okay, then you get the 6 minus 3 cos theta. Okay, then so now I want to get my bending moment, okay, from this 10 kilonewton. So what is my equations? It will be 10 is the force, and then 6 minus 3 cos theta is the length, okay, and then it is acting the same direction, it is negative. So this is how you get a bending moment equations for this section 2.2. Okay, similarly, you can determine for your small m here. Okay, but because this is just a proportionate method, you can just divide by 10, the whole thing, this m. Okay, but if you still, do you understand how to get this distance, my class? The 6 minus 3 cos theta. The rest of the students.
Understand.
Okay, so I will just continue with this small m. The small m will be equal to negative 1. Okay, 6 minus 3 cos theta. Okay, just use this big M divided by 10 because this is you can use a proportionate method. If not, you just carry out again. Okay, by changing this 10 kilonewton become 1 kilonewton. Okay. So now we have gathered all these bending equations. I would like to put it in the table. Okay, can you help me to put in the table? Okay, I have this left. So let's try quickly. The range, okay, I put in x1 is equal to from 0 to 3. Okay, and then the other one is theta from 0 to pi over 2. And then this big M, okay, for this section is negative 10x1. Okay, small m will be equal to negative x1. Okay, and then this one is you can come out later with negative 60 plus 30 cos theta. Okay, and you can simplify here is negative 6 plus 3 cos theta. Okay, then we can go to these equations, applying equations. Keep this first. So I will take this one and then putting here. Now I'm going to write the equations. Okay. At A, okay, using the integration m over ei dx. Okay, so now I'm going to put in, this is AB, this is my BC. Okay, to write it. Okay, so now I will start with AB first. Okay, for part AB, so I will have this integration from 0 to 3. Okay, and then I put in my this multiplication of the moment at the real structure and also my virtual structure, and then dx, and then I need to remember to put my ei. Okay, so the next will be on this. Okay, 1 over ei. This is very lengthy. Okay, so I put it at the back. Okay, E1 over ei, and then this is from theta right now, must be in radian, 0 to pi over 2, and then I have negative 60 plus 30 cos theta, and then multiply negative 6 plus 3 cos theta, and then here, when you are applying this arch problem, I have something new to introduce here. Okay, so now whatever you have practiced before, you are using dx. Okay, dx is just a horizontal or vertical distance. Okay, but when you want to talk about this distance that have radial, radical distance. Okay, we are talking about this. Okay, dx. Okay, so this is we want to use this d theta right now. Okay, so to get this section, okay, you need to change to actually d theta is m over ei r d theta. Okay, meaning that you need to have some treatment here. Okay, dx is actually equal to r d theta. Okay, so now whenever you want to use this arch or angles, okay, you need to put it this r d theta here. Okay, so here there will be maybe just for us to be remember, I will put it here. Integration m over ei r d theta. R d theta. Okay, therefore here there will be another r, right? R d theta. You need to multiply this another one r. Okay, input because you want to use r d theta here. Okay, this is some treatment here. Now you need to be aware. Then you can continue with using your calculator. Okay, can you help me to solve for AB first? Okay. I have an answer here with me. Can you help me? Oh, we are almost the time. Can you do it quickly? So that we can complete this together. Using your calculator, can you get me this section AB, solve for this equation? Anyone? 90 over EI. Thank you. Okay, now for member BC, okay, this is dealing with the radian. Okay, so therefore you need to change your this calculator to radian instead of degree, because we are not inputting the anything about the 90 degree or what. Okay, can you change to radian first before you putting in this equation for BC? Can you try now for me? Change to radian. Maybe I need to put a reminder here for this. Change to radian. Okay, in your calculator. Then you can put input these equations directly in the integration function. So it may take you some time, okay, but I will share you the answer here. You shall be able to get 828 over EI. Okay, then you can sum it up, 918 EI. Okay, so you can try that later. Okay, I hope you can successfully get this, and then don't forget to look at this past year paper, the real past year paper, that we have this P and the R value. Okay, what you should do, you can try it. Okay, meaning that you just put it instead of this value of this 10 kilonewton, you replace with a P and so on. Okay, instead of 3 meter of the distance, you put it as R. Okay, so I'm sorry I've taken another 7 minutes from you. I have to stop now. Okay, if you have any question, you can ask in the WhatsApp group. Okay, so I will see you in the next class.
Yes, madam.
I will share you this piece of writing as well. I mean, my solution. Okay, and you recheck. Huh? Okay. I dismiss the recording.
Okay,
So
madam.
I see you next class. Huh? Bye.
Thank you,
Bye,
madam.
madam.
Thank you, madam.
Madam.
Thank you, 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 madam.
Elvira, you're still here with me. Do you have anything to ask? Elvira? I have to remove you, okay, because I need to leave the meeting.